great. So all of this is fine. So now we will move to how do you find the frequent item sets. So we will make use of something called the a priori property, right. So what is a priori property? Very simple. So you use this idea for pruning the candidates that you will generate while you want to count, right. So most frequent pattern mining algorithms go like this, right. So you start off with a database of transactions, right, and then you generate candidate item sets, okay. These are all the possible item sets that could be frequent, okay, and then you go count them, right, and then based on the counting you can prune away some of those, right. So if you are doing this blindly, suppose I give you a universe of 5 elements, how many item sets can you generate, right. So I can generate 2 to the power of 5 minus 1 candidates, then I have to go count all the 2 to the power of 5 minus 1 candidates, I have to count, right. Okay, 5 is fine. What if you are Amazon? At 2 to the power of 10 million minus 1, right. So that is not going to work, right. You need some very strong way of pruning these things, right. In fact, whatever I am going to talk to you about today will not work if you are Amazon. You need even stronger ways of pruning things. There are other techniques for doing it. So based on this a priori property, right. So people propose something called the right. So a priori algorithm is not the only one that uses the a priori property. A lot of frequent pattern mining algorithms use the a priori property, right, but there is a specific algorithm called the a priori algorithm, right. So what I am going to do, I am going to talk to you about 2 different algorithms for doing this. I will just do this by illustration. I will just take a database of transactions and then I will walk you through the steps for doing this, counting. So I will just write down the database here and right, I am going to say that I require a min sup of 2, okay. So what I will do with a priori, the algorithm proceeds in passes, okay. In pass 1 what will I do, I will find out the frequency of all 1 item sets, right. I will find out the frequency of all 1 item sets. So what will I do here, okay. Right, so we do this is the counts, right. Now what I do is I do any kind of pruning I want. So I throw away all the 1 item sets which have below the minimum support threshold, right. So I throw away I6, I7, all that, right. So none of these will get thrown away, right. So this will all be there. Now what I do is for people who know databases, so people doing databases, right. I do a self join, right, and generate candidates. For people who do not know self join, I basically extend all these patterns by 1, all possible extensions, right. So, why is join an interesting thing? Because join has been highly optimized by the database community. So, if I just say go ahead and do a join, okay, I can compute it much faster than saying that okay, go do a sequential scan of this and extend each pattern by 1, right. So, and I am assuming that everything is commutative. So, I do not have, once I do I1 I2, I do not have to do I2 I1 because they are all sets, right. So, these are all the candidates for the phase 2, right. So, what I do now is I can do a pruning. What is the pruning I will do? So, remember I am going to use the a priori property. So, if this has to be frequent, right, all its subsets have to be frequent. So, what are the subsets of this? Well, I1 and I2. It turns out that since I generated this join from one item set table which are all frequent, so all of the subsets will be frequent. So, in this case I do not have to do any pruning, right, I will just count. So, the counts for these okay. These are the counts for this. Now I can do a pruning. So, anything that is not frequent I will throw out. So, what are the things that are not frequent? That. So, all these have gone, right. So, what I have done here, I have done a count and then I did a prune, right. Now, what do I do again? Whatever is left I do a self join, or for non CS people I extend it by one more, right, provided I1 and I2, I mean, so the first elements are common, right. So, for example, I can do a I1, I2, I3, right. So, I can't do a I1, I2, I4, I can't extend I1, I2 by adding I4 because I do not either have, I do not have an I1, I4, right. Where do I have I1, I4? I have stuck it off.
I1, I2 and I2.
No, I need the first elements to be common. When I do self join, I need the first elements to be common. So, if I want to do an I1, I2, I4, I need I1, I4 here. Since I do not have that, I can't do the I1, I2, I4 join, okay. So, this gives me an additional join, gives me an additional pruning and taking advantage of my set property that the order does not matter. So, I am doing an additional pruning. So, likewise I can do I1, I2, I5, I1, I3, I5, then right. I can do these 6 things, I1, I2, I3, I1, I2, I5. Yeah, I1, I3, I5, I2, I3, I4, it's basically I2, I3, I4, I2, I3, I5, I2, I4, I5. These are the 6 elements I will get after I do the join, right. Now even before I count, I can do some pruning. How? So I look at this, right. So can I prune this? No, I can't prune this, I can't prune this, but I1, I3, I5 I can prune. Why? Because the subset I3, I5 is not frequent, right. Even before I do the counting, I can do the pruning. This is where I use the a priori property, right. What about I2, I3, I4? Can I prune? I3, I4 is gone, right. So I can prune that. What about this? Again I3, I5 is gone, I can prune. What about this? I4, I5 is gone, I can prune. So all of this I prune even before I count, right. So now I only have 2 item sets of size 3, 2 3 item sets that I have to actually go and do the counting for.
So here now if we do the join after counting, should just the first
Yeah.
element be
Will there be a join after this? Yes, I could do a join after this. Right. The join will be I1, I2, I3, I5.
okay, the
First two will have to be common. So I can do a join. So after this I will do a join which will be I1, I2, I3, I5, and will this be frequent? Our friend I3, I5 comes to our rescue, right. So this will not be frequent, so I am done, right. So what are all the frequent item sets? 1, 2, 3, 10. Okay. So what is the big drawback with a priori algorithm is that you do generate a lot of candidates, right, and then you keep pruning them. But even here, even though you pruned a lot of the candidates without counting, but you did end up generating a lot of unnecessary candidates, right, and then you have to go back and verify the a priori property for them and then prune them. That is one drawback. And the second drawback is in every phase you scan the data all over again and you do the counting, right. So when you counted this, okay, you do not somehow save the information for generating this count as well, right. So there are a lot of newer frequent pattern mining algorithms that work on very large data sets, which they try to do it with a single pass through the data. Okay, they keep ancillary data structures around. Okay, they do a single pass through the data and they are able to count for all the frequency. You would think that you need at least 2 passes, 1 pass to generate the candidates and 1 pass to do the counting. There are ways of doing it without actually doing that. The single pass algorithms are available, but I am going to talk to you about a 2 pass algorithm now, right, which is efficient. But everybody get the a priori algorithm, right? It is fairly easy, right? Great. So let us do the 2 pass algorithm now. Look at 2 pass algorithm which we call FP growth. Any idea what FP stands for? Frequent pattern growth, right, FP growth. And so it tries to avoid candidate generation, right, tries to avoid unnecessary candidate generation and minimize the number of passes you go over the data, right. How does this accomplish this? It accomplishes this by creating a data structure called the FP tree, right. So once you created the FP tree, right, once you created the FP tree, you make many passes over the FP tree, but it is somewhat of a compact tree, I mean it is like a not a balanced tree, it is more like a kind of a tree like data structure, if people know that, but you do not have to know that, right. So you just go over the tree. So it is much more compact representation than going over the table all over again, right. So you don't, once you construct the tree can stay in memory, and you essentially go over the tree again and again, right. So let us do this step by step. We will construct the FP tree first, okay, and then from the FP tree we will start generating this, okay. So what we do, first phase is you go over the database once, and then you count. What do you think you are going to count? Huh? The frequency of all the one item sets, okay, that you have to do, there is no other go, right. You count, right. Right, and you sort this by descending order. So let us call this this order as some L, okay. So the L is this ordering, okay. Now what I have to do is go into each transaction, okay, and reorder the items by L, right. So what I do is, okay, you guys can help me out here. So that will become right. So what about this? Fine. This fine. What about this? Has to change. That is fine. That is fine. That is fine. This has to change. Anything else has to change? Oh, 3 and 5 are okay, and this again has to change, right? So I do not have to do a separate pass over this, okay. I can do this reordering as I do my second pass. Okay, the first pass through the data, I count the one item sets. Second pass through the data, okay, I create the FP tree. In the L order. So L order is essentially each transaction I will do this. Now for every transaction I will create a path in the tree, right. So I will start off with the root as some null, okay, nothing, so no items, right. The first transaction is what? So I will label this as I2, I1, I5, right. Is the count, okay, how many times I have seen this? Once. Okay, what is the next transaction? I2, I4, right. So I start off with null set, then I add I2, then I add I4, right. So this is essentially that. Okay, what's the next transaction? I2, okay, okay, anything else? of course a lot more, I2, I1, so I2 becomes 4, I1 becomes 2, I4 becomes 1. Next one is I1, I3 again, no, not again, the first time. So what do I do? Right, and then what do I get? I2, I3. So you can see that I can redo the ordering whenever I read the transaction. I didn't have done it in the first pass, right? So I can do this. Then where are we? T7, right? And T8, it's I2, I1, I3, I5. Then the last one T9 is I2 again, then right. So we have our FP tree, right. So we have our FP tree. So there is only one thing that is needed to complete this. So for ease of navigation, so I am going to have pointers from this table, right. So where does I2 start here? Okay. Likewise, where does I1 start here? Okay. If there is a second entry of I1, this will connect that, right. Then what about I3? So I3 is also connected like that. Then I4, my God, it starts looking very scary, right? This is why I wanted the that is your FP tree, right. So essentially I have constructed this FP tree by doing a second scan over the data, and if you think about it, so if you take any path down this tree, okay, the prefix of the path, that is the things that come at the beginning of the path, will tend to be more frequent than the things that come at the end of the path, right. That is the whole idea behind what we have done with this FP tree. Things that come at the beginning of a path, if you take a path from the node to the from the root to the leaf, right, things that come at the beginning will tend to be more frequent than things that come at the end. So now what we are going to do is we are going to work from bottom up, right, and try to generate an auxiliary data structure for the FP tree, right, from which we will generate the frequent patterns. Okay, we can just read off the frequent patterns from this auxiliary data structure. So what is it that we do? We generate something called a conditional conditional pattern base, right. So we typically do this in the reverse order of our table here. So I will take I5, right. So I look at all the paths that contain I5, right, and take the prefixes of that. prefix of I5. So I will take all the paths where I5 occurs and I will take the prefix of that, right. How many paths does I5 occur here? So I2, I1, I5, right. So that is one thing. So I will just take the prefix. So I2 comma I1 and it occurs once, and then anywhere else I2, I1, I3, I5, yes, that is I2, I3, I1, I am sorry I1 sorry I2, I1, I3. There is a conditional pattern base for I5. Okay, so I took the things that came, right. Now what I will do is I will assume that these are my only transactions, okay, and I will create an FP tree. Right, I will assume that these are the only transactions I have and I will create an FP tree, but before I do that I will ignore all the entries in this conditional base which appear only once, all the items, one item sets that appear only once I will ignore them, right. So I3 appears only once in the whole thing, right. I1 appears twice, I2 appears twice, but I3 appears only once, right. So I will ignore the occurrence of I3. Now I will try to create a FP tree with the remaining two transactions. So what are the transactions? I2, I1 and I2, I1. So my FP tree will look like right. So I look at the path of a specific frequency. So the path here I1, the I2, I1 path has a frequency of 2 and I know that it is followed by I5 because that is how I selected these things, right. So the frequency of I2, I1, I5 will be 2. We already counted that, we counted that by doing multiple passes of the data. So now not only will this give me this I2, I1, I5, it will give me any frequent pattern in which I5 is a part of, regardless of how large the item set is. So it will give me not only the 3 item sets, frequent 3 item sets in which phi is part of, it will also give me the frequent 2 item sets in which I5 is part of, right. So then I can say that yeah. So how do I read the 2 item sets that I5 is part of? Just take any prefix in this path, right, or any combination in this path, right, which has only one thing, right. So not only is I2, I1, I5 frequent, I1, I5 is frequent, I2, I5 is also frequent and the frequency is 2, right. So that is basically done. So I have counted all the frequent item sets with I5. Likewise I can do this for I4. So what are the frequent, what is the conditional pattern base for I4? So this is called the conditional FP tree, okay. This is the conditional pattern base and the FP tree I construct from the conditional pattern base is called the conditional FP tree, and from the conditional FP tree I basically can read off the frequent patterns, okay. So what is the conditional pattern base for I4? Here, so you have to look at wherever I4 occurs, see that is why you need this data structure, right. Just go here, follow that, okay, I4 occurred here, follow that back. So I have I2, I1, I4 occurring once, so I2, I1 occurring once, then follow that there, so we get Okay. Now what can I do? I can ignore I1, right, and I construct my FP3, which is even simpler than this. Conditional FP3 is essentially, so the frequent patterns are I2, I4, right. Frequent patterns are I2, I4. Basically, you are done.
So what if there are many candidates that we can ignore? We ignore all the candidates.
All the candidates.
That appears.
Yeah. So the nice thing is now I can ignore I4 and I5, right. Now I want to go to I3, right. So if you look at it, so there is something beyond I3, but I do not have to worry about it. If this was part of a frequent pattern, I would have already got it when I went back from I5, correct. So when I start now, when I go to I3 and I am constructing the conditional pattern base for I3, I only have to look at the prefix above I3, not what comes after I3. So if there was anything it should have been part of, that should have been captured already. If it hasn't been captured, I do not have to worry about it. And that is why we go from I5 to I2 in this case. Right. So in I3, what is the base? So start off here. So it will be I3, I1, I2, right. So it is essentially I2, comma I1, and the count is 2, because I3 count was 2, right. So the count should be 2. So far we have only had a count of 1, okay, but here the count will be 2. Okay, anywhere else I3 occurs here. So that is basically I2, anywhere else I3 occurs here. Then how is the conditional FP3 look for this? Look like for this? Right. So now again I can read the frequent patterns of this. So what is it? So I2, I1, I3 with a frequency of 2, right. I3, I2 with a frequency of 4, I1, I3 with a frequency of 2 here, 2 here. So I1, I3 has a frequency of 4, I2, I3 has a frequency of 4, I2, I1, I3 has a frequency of 2, right. I can just read it off the tree, okay. So we can check whether that is correct. So I1, I2, I3 has a frequency of 4, I1, I2 has a frequency, I am sorry 2, I1, I2 has a frequency of 4, I1, I3, sorry this one is not done, I1, I3 has a frequency of 4, I2, I3 has a frequency of 4, right. So whatever we counted, but all the frequent item sets that contain I3 are done in one shot, right. Likewise you have to do one for I2 now, I am sorry I1. So what will be the I1 tree? What is the conditional pattern base for I1? I do not have to worry about that, right, because I know the frequency of one item set. I know the frequency of I1 is already 6, I know that. So basically this is the only thing I will get, and so the tree will look like
The count is
4.
I2 appears only once in this time we don't.
What?
I2 appears.
No, 4 times, right. So this path has been taken 4 times, that is what this tells me. So that means I2 I1 should have appeared 4 times. So the prefix I2 ending with the suffix I1 would have appeared 4 times. That is basically what the conditional pattern base tells me. So the conditional pattern base for I1 is just I2 colon 4, and the conditional FP tree is just one node, that is null, and then I2 colon 4, and the frequent pattern so the frequency of I1 I2 is 4, and that is what we get here. I1 I2 is 4, so we get that, right. And of course the one item set frequency is already given to you by the table, right. Do I need to do the conditional base for I2? No, does not matter, right, because I have taken all the other items. So I2 I do not have to actually process separately, right. So what is the nice thing about this algorithm is that I did not have to do a generation of a lot of candidates and then prune things down, right. So I had a way of traversing this tree that just gave me the frequent item sets, right. That is one thing. Second thing is I just did 2 passes over the data. All subsequent passes were done on the tree, right, and the tree is somewhat compact, right, assuming patterns actually repeat, right. I mean, if the patterns do not repeat at all and every transaction is a unique subset, then you are doomed, right. So you will get a very large tree, even that will be slightly compact, but still it will still be a large tree, right. But since patterns repeat typically, right, so you are safe. Okay. So any questions on how this happens? Right. So first you do one pass through the data, right, count the frequency of one item sets, right, sort them, then do a second pass through the data, construct the FP tree, right, put in all this navigation links, right, and then for each one item set construct a conditional pattern base, and then construct a conditional FP tree, and from that you can read off all the frequent item sets that contain that item. Okay. Make sense? Any questions on that?
Can you please clarify the part where we prune away some of the labels after we find all the paths?
Good point. So I have done this I5, right. So I basically I computed the conditional pattern base, right. So if you look at I3, right, it occurs only once in the entire conditional pattern base, right. So I can prune it off. So now my conditional pattern base will actually become I2 I1 colon 1 and then I2 I1 colon 1. So I will just create my tree based on that.
So that one is decided by
Sorry?
So that min is decided by this min sub, right?
That is decided by min sub, yeah. That is decided by min sub. So whichever occurs less than min sub number of times in this, I will remove it, because it can't figure in a frequent pattern. Right, so that one, oh okay, you are confused about the one, is it? No, it is min sub. Anything occurs less than min sub, because min sub is 2 here, so it just becomes 1. So anything that occurs less than min sub number of times, it will. So we can rework the whole thing, setting min sub to 3, right? And then you would see interesting things, right? So I mean, all of this will go. There will be no frequent pattern of length 3, right? So both of this, the I5, I4 will go, right? I4, I5, yeah, I5 no will all go, I4 will all go, yeah, that's correct, right? So I4, I5 will all go. Right? There will be no patterns that feature I4 and I5. In fact, they will go from this table itself, because they occur only twice. So you only have 3 entries. So if we start off with a frequency of 3, you only have 3 entries in this table, right? So your everything becomes simpler, right? Okay, that is a good point. So if you start off with only 3 entries in this table, when you construct the FP tree itself, so you leave out I5 and I4 from the transactions there. So these entries will not even be made. This I5, I4 entries will not even be made. Right? What you will do is, if some things get dropped out because the one item set is not frequent, right, I will delete them from the transaction order also. So I have sorted them in the decreasing order of this table, right, and whatever is below the threshold I will just delete it, right. So T1 will become I2 I1, right, and T2 will become just I2. okay. So that will not even figure in the IP in the FP tree construction. Okay, any questions?
Are there any approximation algorithms for frequent pattern mining?
Yes, there are algorithms that use hashing, and in fact I take it back. So even the algorithms that use hashing actually give you the right count, but there are algorithms that give you an approximation. But there are so many efficient algorithms that give you exact counts nowadays that use hashing that I don't know if you should be using approximation, but there are other approximation algorithms for this. Yeah. See, the more interesting research question to ask now is what happens if I am not just counting elements, if I am not just counting subsets. If I am counting data with additional structure in it, right? So that's a more interesting question to ask.